Hi everyone, welcome back to the third day of the H0 2020 conference. If you'd like to turn on your video and audio, we can say hi to each other. Welcome back. So I'm Sherry Suyu from the Max Planck Institute for Astrophysics and the Technical University of Munich. I'll be chairing today's session. Here is the program for today. So again, we have an excellent lineup of speakers, and just a reminder for those who haven't used it yet, each on the program, so you can find the program on the website at the top here, and next to each speaker, there's a Q&A link that goes to the Slido where you can type your questions. And if you type them early, that also gives people time to upvote your questions that we can then ask at the end of each speaker's. And this is basically what it looks like on the Slido. Many have already used it in the past couple of days, but this is just a quick reminder. And that's all for in terms of announcements from our side. And our first speaker today will be Tamara Davis. So I'll stop screen share. And when Tamara is ready. Tamara, are you there?
So should I get going straight away?
Yeah.
Awesome. Okay, so let me just share my screen.
Great, thanks. So I'd like to ask then people to turn off their videos and speakers.
Can you see my screen?
Great, thanks.
Yep, excellent. Okay, so first things first, thanks heaps for the organizers, for putting this on, even though we're all speaking remotely. It's actually really fun that we can get lots of people coming here that would not otherwise have been able to listen to the talks in person. So thanks very much for that and for inviting me to give this talk. I am going to talk about redshift measurements, and we've been hearing some fantastic talks about the basically superhuman efforts people are going into to calibrate distance measurements of various types. So I thought that it would be good to pay a little bit attention to the other axis. If we're measuring the Hubble constant, we need to know not only a distance measurement, but also essentially a velocity, which we get via a redshift. So are there any uncertainties in the redshifts that we should worry about? And we've been able to measure redshifts so accurately for so long that usually in our cosmology analysis, if we're using spectroscopic redshifts, we don't even bother to put an error bar on the axis. So is that a problem? Let's have a little look. So before we start, if we're having this conference in Australia, and especially in the context of Black Lives Matter at the moment, we would usually have one of the Aboriginal elders come and give a welcome to country. And when we're giving talks in Australia, we always start with an acknowledgement of country. So we acknowledge the traditional owners of the lands on which we're speaking. And today I'm in Brisbane, and that's the Turrbal and Yagara nations. And so I'd like to pay my respects to the elders past, present, and future. There's something really cool about Aboriginal astronomy as well. If you think about the constellations, as I grew up thinking of the stars as pinpoints of constellations. Here in the Southern Hemisphere, since we've got such a beautiful Milky Way, one of the things that the Aboriginal people did was made stories and constellations up about the dark patches as opposed to the stars, which I think is absolutely beautiful. Okay, so big question of the day. Could redshift errors be biasing our measurements of H0? Short answer, yes, but they're unlikely to be sufficient to explain the H0 tension. Nevertheless, there are common errors in redshifts that we do need to fix, and I'm going to try and point out a couple of those now, how they're being fixed and what we need to worry about for the future. So firstly, how large a redshift error would actually matter? It turns out that surprisingly small systematic errors can make a difference if they're at low redshift. And you can see that in this Hubble diagram. You've got the distance modulus versus redshift. most of the effort goes into measuring either luminosity distances or angular diameter distances of various sorts that can go onto a diagram similar to this. And the main problem here is at low redshift, if you shift the redshift by just a little bit, it actually gives you a really big jump in magnitude. And so the point where redshift errors are the most problematic could be at low redshift. And to demonstrate how small an error matters, I've taken one of these curves here, just added a redshift error of various sizes that's systematic across all redshifts, and just shifted this curve across and seen how much of a jump in magnitude you get. That's on this plot here, where you see the difference in magnitude you get for various different shifts in redshift. The green line is a shift of 10 to the minus 3, which is a reasonably big redshift error, but as we'll see, that kind of thing pops up fairly frequently in measurements. And the orange is a redshift shift of 10 to the minus 4. For comparison, this is just the magnitude difference you get. For comparison, this is the horizontal lines of the magnitude change that you get for different changes in Hubble's constant. So you can see that at redshift of 0.04, a redshift error of 10 to the minus 3 would mimic a Hubble constant difference of about 2 kilometers per second per megaparsec. So if we want to keep our Hubble constant errors low, we need to control systematics at a level better than that, preferably at the level of about 10 to the minus 4. Random errors in redshifts used for cosmology are usually quoted on around with uncertainties of a few by 10 to the minus 4 to 10 to the minus 3, sometimes more accurately than that. Now you can measure redshifts really, really accurately if you want to, but it takes some effort. If you're doing it for planet finding or for variations in the fine structure constant and stuff, you can get 10 to the minus 6 without too much trouble. But it's a lot more effort than the kind of effort that we go to for the redshifts we take for cosmology usually. If you want more detail, have a look at this paper that I wrote with some colleagues last year. It gives a little bit more detail of the kinds of things that we're looking at. Now, I thought it'd be fun to show a bit of actual data. Here's a spectrum that you get that we took for the OSDES program that's getting redshifts for the Dark Energy Survey Supernova program. And here is a beautiful emission line spectrum in green. And what I'm doing right now is I'm flicking between two different redshifts that differ by a factor of 10 to the minus 4. So if you're not seeing a hell of a lot of change, it's not because Zoom has frozen, it's because there really is not a lot of change going on here. If you look at the bottom right, you can see a zoom in on H alpha, and you can see that it's changing by sort of almost a pixel. And if I go forwards one more, I've now superimposed two green lines on top of each other. If you look at the very bottom left, you can see O2, and you can see that there's you can almost see the difference between the lines there. So a 10 to the minus 4 redshift error is really small for data like this. There's a couple of interesting things in this data. Unsubtracted skyline, that's not a problem. We know how to deal with those very well. But you may have noticed this weird thing going on here where once we line up H alpha and H beta and O3 with where we expect them to be, you can't simultaneously fit O2 as well as these lines. And that's because in this case, it doesn't happen that often, but in this particular case, there's been some sort of wavelength calibration error. And the wavelength calibration error that we're seeing is something on the order of 2 by 10 to the minus 3. If this was in a subset of our data, and we actually focused on, here we don't necessarily know which line is wrong, it's probably this one. But if that kind of thing is the thing that me as someone who is helping run a redshift survey started to really worry about. Okay, so what other sources of redshift bias could we have? We can have observational errors. I'll mention a few of those that are possible. We can also have physical effects like gravitational redshifts and peculiar velocities of various sorts. And we can have theoretical errors. And I put these in the facepalm category because we really shouldn't be making these, but it turns out we actually are making some of these. So I'll go through a couple of these and how we should avoid doing that in the future. Okay, so observational errors. We've got the sources of error that we can look for. There's some that are random. If they're random, we don't care that much. They'll average out. It's the systematic ones that we really worry about. There's a couple of interesting ones. So again, this is the paper that I wrote last year, outlines these in detail, and I encourage you to go there if you're really interested. Some potential things like line smoothing. If you have a line on a continuum that has a slope, the center of the line gets slightly biased. For example, if you're at the 4,000 angstrom break, that could cause something that might be systematically biased. The spectrograph wavelength calibration I've already mentioned. I had a minor panic briefly about the air to vacuum conversion, because it turns out that at 3,000 meters altitude, the refractive index of air is 10 to the minus 4 different than it would be at standard temperature and pressure. But as long as then I realized that as long as you do your calibrations in the same conditions as your measurements, everything should be okay. So that shouldn't be a problem. But there's a whole bunch of things that go into redshift measurements that are things on the order of 10 to the minus 4. Hopefully none are serious issues, but we can do a bit better at looking at it carefully. Now onto physical effects. Firstly, gravitational redshifts. We wrote this paper in 2015, just looking at the gravitational redshift experienced by a photon while it travels. And here on the left, this is just a slice through a simulation where we watch the gravitational potential that the photon experiences during its path. And the long story short, if you're in a cluster or in a void, all of the photons that are arriving at you will be shifted by something on order of a few by 10 to the minus 5. So what that means is the gravitational redshifts that we expect in a normal lambda CDM type of universe should be too small for us to worry about. So those are relatively small errors. On the other hand, peculiar velocities can be quite large. So if you're looking at peculiar velocities, one thing I'm going to concentrate a bit on later is the heliocentric correction, which is our own motion. If you look at peculiar velocities, examples are things like the order of magnitude that you might get. The Earth going about the sun is about 30 kilometers per second. So that's about a 10 to the minus 4 redshift. The sun going, but usually we're observing perpendicular to that, so it's not too important. The sun going about the galaxy is about 260 kilometers per second. The galaxy with respect to the CMB is about 600 kilometers per second in the other direction, approximately, which means that when you measure our motion with respect to the CMB, we're at about 370 kilometers per second, which has been measured really well now by Planck. We also have the peculiar velocities of the distant galaxies as well that could cause problems. So I'm going to talk about the heliocentric correction later, but I thought I'd jump in and give one example of a case where peculiar velocities matter for an H0 measurement. And that's this absolutely fantastic measurement from gravitational waves. I was so excited to see H0 being measured by gravitational waves. Here's the plot that was from the famous first bright siren that we get, and we'll see Bernard's talk later in this session to have more about this, and also the dark sirens, presumably. And so this is a very nearby source that and H0 was measured to be about 70 plus or minus 10-ish kilometers per second per megaparsec. And in this measurement, a peculiar velocity correction had to be made because you've got the nearby source, it's moving around. And if you look at how it's actually done, you look at the velocity of the group that the gravitational wave came from. If you actually took that as the raw measurement, you'd end up with an H0 of about a peak H0 of 76 kilometers per second per megaparsec, just going really roughly. They then look at the peculiar velocity by mapping the velocity field and look at what component of that velocity is not due to the expansion of the universe, but just to peculiar velocities. That gets subtracted off, and that would give a peak of about 69 kilometers per second per megaparsec. It's not exactly 70 because the peak is not exactly where the best fit is, but the ballpark estimate for what the peculiar velocity correction is about 7 kilometers per second per megaparsec, which is really huge. So we had a look at this because we've been working with some peculiar velocity surveys, and just the values of the peculiar velocity correction that are used in this example. And if you look at all of the possible different catalogs that were used, different groups that could have been chosen and that kind of thing, the velocity that was used for the CMB frame, CMB frame redshift was one of the higher ones that was used here, while the peculiar velocity one is one of the lowest ones that could have been used. And so Cullen Howlett did an analysis where he looked at all of the different possibilities and tried a variety of different models that could have been used for the peculiar velocity here. And the original fit is here in blue, and Cullen did a Bayesian average of all of the different peculiar velocity options that we thought were viable. And the Bayesian average, you can see that the original is basically on the high end of all of the possible options. And so this could put the central H0 value a bit lower. Same thing happens if you can use the different analysis with the viewing angles constrained. So this is the result of that quick analysis, that the Hubble constant is about 3 kilometers per second per megaparsec lower, which here, because the error bars are large, is a difference of less than half a sigma up to a sigma if you use the more constrained angles. Now, it's really important to note that this is only because it's one object and it's at really low redshift. Peculiar velocities will tend to average out as you get more redshifts. And so this, you'll have some moving away, some moving towards, and those will cancel. So that's reassuring that this is not going to be as big an issue for this for gravitational waves as this goes on, because the same thing happens for supernovae and any standard candle or ruler if they're close enough. Cool. So now let's go on to some of the theoretical errors that could be in there. And the number one that I want to make sure that everybody stops doing is adding redshifts. So if we look at the redshift that we measure, so imagine here galaxies 1 and 2 are co-moving galaxies, and galaxy 0 has some sort of peculiar velocity relative to galaxy 1. The redshift that you observe is not the sum of the redshift due to the expansion of the universe and the redshift due to the peculiar velocity. The redshift that the definition of redshift is up here. It's the difference between the observed and emitted wavelengths. If you, and I was going to say that if you use this for heliocentric corrections, you get some quite large errors, and this is very common. So to explain why this is wrong, just really quickly, this is how 1 plus Z is the ratio of wavelengths. If you want to compare two different things in 2 steps, you can basically chain rule it. And so you need to multiply factors of 1 plus Z. So that means that if you look at the observed redshift, it's a combination of the recession and peculiar redshifts, but in this multiplicative factor. And if you use the additive low redshift approximation, you forget about this term here. Now, the motion due to our galaxy is about 300 kilometers per second. So it's about a 10 to the minus 3 contribution. And so if you multiply by the recession redshift at a redshift of 1, that's going to be a systematic 10 to the minus 3 error. Now, as I said, this is very common. This is used all over the place. If you look at the NASA Extragalactic Database, the velocity calculator provided there uses the additive value. And so my student, Anthony Carr, has been doing some analysis of this, and we're working with Ned to fix this, but also to look at this in supernova samples and make sure that this isn't causing a problem. And so here is a plot of where we've compared the full correction using the multiplicative factors to what's seen in Ned, where the data points here are just the values in Ned, and this sinusoidal factor is what you would expect to see as you go around in different directions on the sky. So this is as a function of direction on the sky. So if you look at supernova samples, you can also see that the additive correction is usually used in supernova samples, but also that there's as much up as down, so it mostly will cancel out, just like peculiar velocities will cancel out in most cases. It's only if you're looking at a particular direction of sky that this is going to be absolutely systematic. But when Anthony was looking at this, he did see some other interesting features as well. There's a couple of weird outliers that are have bigger things than you expect, and some weird ones hanging out over here. And he separated it by different samples here. And it turns out that there's a couple of weird things going on. This is an example where the heliocentric correction was done backwards. The candle supernovae, which are here, you can see them separated by sample. Some of them have Z helio and Z CMB all done the wrong way or swapped. And some had rate ascension and declination incorrect in the files. So there's a few different things that need cleaning up. But the long and the short of it, when this is done, is that the errors are mostly negligible. Everything where there was a big error is at high redshift, where it doesn't matter so much. And even for this one, where you can see there's about a 10 to the minus 4 shift in the SNLS mean, because they were in specific regions of the sky, since that's at relatively high redshift, it also doesn't matter so much for our purposes. So that's reassuring, but it's also something that we can fix. This becomes even more important if you're doing things like time varying dark energy. So rather than H0, we need to fix this for things like that. Since the redshift addition error gets worse as you go to higher redshifts, it's important to ask whether this affects the higher redshift things like the baryon acoustic oscillations. And so I've got another student, Aaron Glanville, who's been looking at this, and we took mock catalogs for baryon acoustic oscillation, shifted the redshifts, added a bias, and to see if there was any effect. The short answer is, again, that since it's at high redshift, the biases don't matter quite as much. And also BAO, interestingly, because they're done relative to a fiducial model, can sometimes be protected by from big shifts because they're looking at differential effects. And if you've done the same thing to your fiducial model as your data, you can actually sort of measure a incorrect length with an incorrect ruler and get the correct answer. So that's sort of a robustness to the BAO in that sense. Okay, so almost done. I was just going to mention that there's, related to the peculiar velocity corrections, there's another physical effect that could be systematic, and that's bulk flow overcorrection for nearby things. So if we take, if we do the heliocentric correction and apply that to nearby galaxies, on average, the nearby galaxies actually share some of our bulk flow relative to the CMB. And so we're going to actually, we shouldn't actually be correcting to the CMB frame because they're not in the CMB frame, they're moving with us. And so we could be overcorrecting their redshifts. And that's another potential redshift thing that we have to worry about. So just to wrap up, I'll tell you the reason why I started worrying about redshifts. And that was because I was looking at the measurements of the discrepancies in H0 and noticed that the things that you measure with luminosity distance tended to be the ones that had, say, high H0, and with angular diameter distance, where you had standard rulers, it tended to get low H0. And the fact that to get a luminosity distance, you multiply by 1 plus Z, and to get an angular diameter, you divide by 1 plus Z. I thought, well, maybe there's something in the redshift that's causing this discrepancy. The strong lenses, which we'll also hear about, is sort of change that though, because when these are included, these are essentially, even though they look, the equation that comes out most often has a multiplier by 1 plus Z factor in it. If these are angular diameter distances, so it turns out that this is actually more like a dividing by 1 plus Z. And they also are tending to find a high H0. So this means, so those are rulers, and that, so my theory that maybe candles versus rulers was the thing rather than nearby versus distant or local versus global might not be, is less likely than it was when I started to look at the redshift issues. So my conclusions are that there are very common systematic errors in redshift that we do need to fix, but that these probably are not causing the H0 tension. Nevertheless, more analysis is worthwhile, because if we're putting all of this effort onto the vertical axis of our plots, we better make sure that our horizontal one is just as good. Thanks.
Thank you. So we have some questions on Slido. First question is from Richard, our co-host. How concerned are you about systematic differences in the experimental setup of redshift measurements in the various available catalogs?
I think that we actually do need to go back and pay attention to some of these. So I've got a program going at the moment, again with Anthony Carr, my PhD student, who is re-observing some nearby galaxies, the ones that are most likely to have a large effect on H0, and reanalyzing the redshifts and trying to make sure that we haven't got any systematics there. So that we don't have, if there's outflows, or we're using an arm of a galaxy that's rotating towards us and we haven't nailed the center of the galaxy, we could have some redshift errors. But also just looking at the calibration of the spectrographs and making sure that there's no systematics there. Also by looking at the variations between redshifts taken from different surveys, that could also be quite revealing. And interestingly, if you look at in NED again, if you look at the history of redshift measurements, you can see that the error bars that people put on them are over-optimistic, shall we say, because you can tell that the variation in the measurements of redshifts are bigger than you would expect by statistical variations given the size of the error bars.
Next question is from Anonymous. How correlated are the various different sources of ocular velocities for NGC 4993? That is, if come from via Tully et al., not so independent?
I can't answer that particularly clearly. There was a variety of, there was some very different measurements there that are completely independent, I think, but some of them will be correlated. Some of them also had subsets of the same galaxies in them. So when Cullen did the Bayesian averaging of these, he took into account some of those possible correlations.
And final question from Matthew Collis. How precise do peculiar velocity estimates for galaxies need to be in order to contribute subdominant errors to low Z gravitational wave siren distances?
How precise? So I have to think about that to get a number, but so they're about half a sigma at the moment at the current precision. So we need to make it. Oh, sorry, no, that's overestimating. Matthew, I'll have to think about that in detail. But what I can say is that one of the things that I think that we could do right now that would help a lot of different measurements is to have a better understanding of our local environment. So if we had a better peculiar velocity map of the local universe, a better density map, we'd be able to diagnose whether we're living in an over or under density, even a slight one, to be able to better constrain outflows and inflows nearby, or Hubble bubble issues, gravitational redshifts, and also these peculiar velocity effects. I think as we get more and more precise, we're no longer going to be able to just sort of sweep that under the rug and ignore it, as we have in most of our analyses so far.
All right, thanks, Tamara. Our next speaker will be Kenneth Wong. He will tell us about H0 from strong gravitational lenses.
Okay, can you see my screen?
Yes, we can.
Okay.
Right. Thanks.
Okay, so yeah, thank you to the organizers for inviting me to give this talk. I will be talking about H0 from lens quasars on behalf of the Holy Cow and TD Cosmo collaboration. So as we've heard the last few days, the reason we're all here at this conference is because of this tension in H0 between CMB measurements from Planck. They find about 67 kilometers per second per megaparsec in the context of flat lambda CDM. And that's in tension with independent results, particularly from the Hughes collaboration, they find about 74 kilometers per second per megaparsec from the distance ladder. So this 4.4 sigma discrepancy, it could be due to new physics, or of course, it could be due to systematic errors. And we heard a bit on the first day about the need for more independent measurements of H0 in order to shed light on this discrepancy. So I'm going to be talking about one of these independent measurements today. And our method is based on gravitational lensing. So gravitational lensing is what occurs when you have a chance alignment of a massive foreground object, which we call the lens. It could be a galaxy in this case, and a background object, which we call the source. So this simple diagram is showing the lensing configuration. Here is the observer, here is the lens, and here is the source. So the source will be emitting light rays in all directions. Some of them will pass close to the lens and will get deflected by gravity towards the observer. So when we look out into the sky, we see something like this. So here is the lens galaxy, and it is lensing the background source into this magnified arc here. So these are actually multiple images of that same background galaxy, but it's been magnified and distorted by the lensing effect. So what we can do is we can ask the question, what is the mass distribution of the lens that gives rise to this image configuration that we see? So in other words, if we were to undo the lensing, reverse the lensing effect, can we get a coherent image in the source plane by fitting a mass model to this lens? So this is a process we call lens modeling and allows us to determine the mass distribution of the lens. So the lensing effect depends on the mass distribution of the lens. It also depends on line of sight structure because lenses are not isolated. All of the mass along the line of sight contributes to the effect. And it also depends on cosmology. And it's that which we exploit to determine H0 from gravitational lensing through a technique called time delay cosmography. So when you have multiple images due to gravitational lensing, such as this situation here, so here is a lens quasar, here is the lens, it's a massive elliptical galaxy, and here are two images of the same background quasar. It's being lensed by this galaxy. There is a time delay between light rays that arrive from one of the images compared to light rays that come from the other image. And this is because light rays that came from this image took a slightly different path through space-time and went through a slightly different gravitational potential than light rays that came from this image. So two light rays that get emitted from the source at the same time will arrive at the observer at different times, depending on the image that it went through. And the expression for the time delay is given by this equation right here. And we can break this equation into two parts. So this first piece, which is a ratio of angular diameter distances, these capital Ds here, this first piece we call d delta t, the time delay distance. So it's a ratio of angular diameter distances, and the factors of H0 in this cancel out such that d delta t is inversely proportional to H0. The second piece of the time delay expression is this piece here, which we call the Fermat potential. So this comes from both the difference in path length that the light rays take, and also the difference in gravitational potential that the light rays go through, depending on which image you observe it at. And you determine the Fermat potential from the lens modeling procedure I described earlier, fitting this mass model such that you can reconstruct the background source. So the idea behind time delay cosmography is that if you can determine the time delay of a lens and you get an accurate lens model to determine the Fermat potential, you can solve for this time delay distance term and therefore solve for H0. So if your background source is variable, such as a quasar, you can actually monitor the lens to directly measure the time delay. So quasars are variable on short timescales. They're bright and easy to detect. And if you just monitor them by taking an image of a lens quasar every night or every few nights, you can build up light curves and look for features in the light curve that correspond to the same source event, but that are shifted in time. So this short movie here is showing, this is based on real data. So here's a lens quasar, and you see over time, you're just taking an image every few nights and measuring the brightness. And you see at some point, the light curve went up. So there's going to be a brightening event right here. And you see it first in image B, then image A, then image C, then image D. And that difference in arrival time is due to this time delay effect. And that offset, so we fit curves to these light curves and then shift them to get those features to match up. And that's how we determine the time delay of the lens. So again, quick overview of time delay cosmography. To constrain the time delay distance and therefore determine the Hubble constant, you need to measure the time delay through that procedure I just mentioned. You need an accurate lens model to determine the Fermat potential, this phi lens term. You also need to estimate the mass along the line of sight, because this can bias your determined time delay distance. So there's this term called external convergence. We represent it with this kappa x. That is actually a direct bias on the time delay distance if you don't make a correction for mass along the line of sight. So you need to estimate that. And you also need the lens galaxy velocity dispersion, because this helps to mitigate some degeneracies in the lens modeling. And you can also get some complementary constraints on the angular diameter distance to the lens if you have that information. So the theory behind time delay cosmography is actually very old. It was first proposed by Refstal in 1964. And that was 15 years before we even observed the first gravitational lens. So people have known about this technique for a long time. And because it's been around so long, there have been a lot of past attempts to use lens quasars to determine H0 with time delay cosmography. Unfortunately, if you look at some of these early studies from like the 1980s and 1990s, a lot of them had various problems, including things like poorly sampled light curves. So there were disagreements about measurements of the time delay. The lens models were often constrained just using the quasar images, so not enough lens model constraints. So you had to make some simplistic assumptions about the lens mass profile. And essentially people sort of ignored effects of line of sight structure. And so if you look at some of the results from these early papers, there's fairly large discrepancies in the results that they get on H0. So unfortunately, I think in the early days, time delay cosmography had a bit of a bad reputation within the cosmological community. But since then, the data have gotten a lot better. The analysis methods have greatly improved. And we think at this point that time delay cosmography is at a point where it is now a competitive cosmological probe. And this has culminated in our recent project, Holy Cow, H0 lenses in Cosmograil's wellspring. So what Holy Cow is doing is a detailed analysis of several time delay lenses using a large volume of data from different sources. So we have long-term monitoring from the Cosmograil collaboration, as well as VLA data to get accurate time delays. We have high-resolution imaging to do detailed lens modeling. We have wide field imaging and spectroscopy to characterize mass along the line of sight to correct for this external convergence factor. And we have conducted spectroscopy to measure the velocity dispersion of the lens galaxies. So in our latest milestone paper, we have analyzed 6 lenses, these 6 that I'm showing right here. A 7th lens has also been analyzed, and I will mention that towards the end of my talk. So now I will just briefly step through the different aspects of the Holy Cow analysis and how we put all of this together to get H0. So the first is the time delay measurements. So we use data from the Cosmograil collaboration. They have been using a variety of small 1 to 2 meter class telescopes around the world to do long-term monitoring of several lens quasars. And they've been doing this for over a decade now. So if you compare some old light curves, like for example, here's an old light curve of a lens quasar, you see it's not very well sampled. Maybe within one observing season, there's of order 10 observations. Now with Cosmograil, they're really doing this in a systematic way. They have observations every few nights. And this particular light curve, they've built up over a period of 14 years. So it starts in 2004, stretches all the way to 2018. And you can see some pretty sharp features in these light curves, and they've developed some well-tested algorithms to do the time delay measurements. And they're able to get time delay measurements down to a precision of roughly a day or so. You do need to monitor for several seasons to minimize the effects of microlensing, although we are working on some high cadence monitoring, and the early results from that look promising. So potentially in the future, we could determine time delays with high precision from just a single season of monitoring. The next part of the analysis is the lens modeling. So we use deep HST and adaptive optics imaging to get an accurate lens model. So just for comparison, here is an old ground-based image of a particular lens in our sample, PG1115. So you see, all you can really see here are these blobs representing the quasar images. So if you were to try to fit a lens model to this, you can only really use the quasar positions as constraints on your model. Now, if you compare that to our data, this is our imaging. Here's HST on the bottom and AO on top. This is the same lens here. Now what you can do is not only do you have the lens quasar images, but if you look very closely, you see kind of a faint ring underneath there and faint ring underneath here. That's actually the host galaxy of the lens quasar. So if you subtract off the quasar light, you actually see the surface brightness distribution of the host galaxy of the quasar, and each surface brightness pixel in that ring gives you additional constraints on your lens model. So rather than just 4 quasar image positions, you have potentially hundreds of surface brightness pixels to constrain your lens model. And by doing this and combining with the velocity dispersion of the lens galaxy to reduce model degeneracies, we can get much more accurate Fermat potentials from our lens modeling compared to the early days. And then there's mass along the line of sight. So I had said earlier that these past analyses basically ignored mass along the line of sight because it was thought that this was a few percent effect. And at the time, that was subdominant to the other sources of uncertainty. But now we're at the point where we're trying to do precision cosmology. This is something we have to worry about. So it's known that lensing is biased towards more massive galaxies. The more massive a galaxy is, the more likely it is to be lensing something. And those massive galaxies tend to lie in overdense environments. So lenses in general tend to lie in overdense lines of sight. So what we do is we take wide field imaging and spectroscopy of galaxies in the fields containing our lenses. And we look for groups and clusters along the line of sight, and we get redshifts for some of the more nearby perturbers to the lens. So some perturbers are strong enough, they're either close enough to the lens or they're massive enough that we need to include them explicitly in the lens model as a mass component. And we use our spectroscopic data to do that. But all of the other galaxies in the field contribute as well. Even if we don't include them directly in the lens model, they're still contributing to this external convergence term that we have to correct. So the way that we correct for that is we use a weighted galaxy number counts method. So we count up galaxies and apertures around the lens galaxy and say, how overdense is this field compared to a random line of sight in the universe? And then we can go to a cosmological simulation, pick out lines of sight in the simulation that have similar relative overdensities. And then in the simulation, we know where all the mass is. So then we can use those lines of sight to constrain the external convergence distribution. I will say that we have also done an independent weak lensing analysis to constrain the external convergence in 2 of our fields. And in those cases, the weak lensing analysis and estimate of external convergence agrees with our weighted number counts method. And then finally, our analysis is performed blindly with respect to H0 and related quantities. So what that means is throughout this procedure, anytime we're analyzing a lens and we look at plots or results, we don't actually look at the value of H0 or time delay distance that we get out. We can look at the width of the distribution, and we can look at correlations with other parameters, but we always blind the result by subtracting off the median. And the reason we do this is just to avoid confirmation bias. So if we think that if we get to a point in our analysis where we get an H0 of say, 74 or 67, we might think that we're doing okay and we can stop our analysis. But by blinding the analysis and not looking at the absolute value, it forces us to be very thorough and very confident in our systematic error checks. And only after everyone in the collaboration has agreed, we decide to unblind, and then we decide to publish the result as is with no further modification. So there's no iteration, like we look at the result and then do more work. Once everyone agrees to unblind, we unblind and then publish as is. Okay, so now I will talk about our latest results. So in our latest milestone paper, we have combined 6 lenses, and we have determined that in a flat lambda CDM cosmology, H0 is 73.3 kilometers per second per megaparsec. This is a 2.4% precision measurement. So in this plot, I'm showing the individual constraints for each of the lenses in the colored curves and the joint constraint from all 6 lenses as this solid black curve. So this is more in agreement with the shoes distance ladder measurement than it is with the Planck CMB measurement. And individually, the Holy Cow result is in 3.1 sigma tension with the Planck CMB result. Between Holy Cow and shoes, these are completely independent methods. They share no systematics, and they are both late universe probes of the Hubble constant. So we can combine them, and we get this purple point here. And in combination with shoes, we find that we have a 5.3 sigma tension between early and late universe probes. And again, these methods are fully independent of each other. So I'm running low on time. So my last couple of slides, I will talk about the future of time delay cosmography and our collaboration. So, so Holy Cow has sort of evolved into a new collaboration, which we're calling TD Cosmo. It's sort of Holy Cow plus Cosmograil plus Strides plus a few other collaborators. So all future publications will be under the TD Cosmo label. We have analyzed a 7th lens in the sample. That's this lens right here. This was work done by Anwar Shajib. And the result he got from this is 74.2 kilometers per second per megaparsec. So it's right in line with the first 6 lenses. And this is actually the most precise constraint to date from any single lens in our sample. We have also done a lot of systematics tests, including things like model assumptions, our line of sight correction, things like that. This was work led by Martin Milan at EPFL. And we found that at least at the level of precision that we're claiming right now, there's no evidence for unaccounted bias or errors. So the individual lenses and their H0 posteriors, there's no evidence that there's some hidden source of uncertainty that we're not accounting for based on their spread. We are also currently working on a joint hierarchical analysis of the entire sample. This is something being led by Simon Beer, who will participate in the discussion panel later. So he'll say a little bit more about it. But essentially, we can relax assumptions on the mass profile and do a joint hierarchical analysis using additional lensing and dynamics constraints from other lenses, such as the SLAC sample. The eventual goal of time delay cosmography is to get down to about a 1% precision on H0. So we think that at the current level of precision per lens, this is going to take about 30 to 40 lenses, or we could improve the precision per system. One way we could do this is through resolved kinematics. So I'll refer you to work done by Akin Ildirim, doing some forecasts using JWST IFU observations. So there are a few different ways we can go to get to this 1% precision. At the moment, the number of known lens quasars is still small. It's of the order 100, but eventually we'll get to the point where LSST and Euclid will find potentially thousands of lens quasars and maybe even potentially lens supernovae to do time delay cosmography in the future. So just to summarize, time delay cosmography is a completely independent determination of H0, independent of the CMB and the distance ladder. From a blind analysis of 6 lens quasars, we find H0 is 73.3 kilometers per second per megaparsec in flat lambda CDM with a 2.4% precision. This is consistent with the shoes distance ladder measurement and in 3 sigma tension with the Planck CMB value. We've analyzed the 7th TD Cosmo lens with more to come. And in combination with shoes, we have a 5.3 sigma tension with Planck between the late universe probes and the early universe from Planck. We've done extensive testing of our model assumptions, and we have a future hierarchical analysis of the entire sample upcoming. And in the future, larger lens samples and new methods will push towards a 1% constraint on H0. So with that, I will stop and take questions. Thank you.
Thank you, Ken. some questions. So first one is from Benan Javan Marty. What is the impact of the lens model on the final H0 value? Is the lens model cosmology dependent?
So we sort of have two different types of lens models that we use. One is a power law model, and one is a composite stars plus dark matter model. And so first of all, both the analysis done in the first TD Cosmo paper shows that the result for H0 you get when you isolate them, like you only look at the power law models or only look at the composite models, is very similar. So the result does not change depending on which one of those model families you focus on. Now, of course, there are potential other model families you could choose. That's something that I think will be addressed in this upcoming work by Simon Beer, and I think we'll talk more about that in the discussion section. What was the second part of the question?
Is it cosmology dependent?
So we do analyze other cosmologies, extensions to flat lambda CDM in our recent milestone paper. As far as differences between the power law and the composite model in the different cosmologies, I don't believe that there are. I don't know if we looked specifically at that in the extensions, but at least for flat lambda CDM, they were the same. And it didn't seem like there was any indication of significant differences, at least in like the residuals or the fits.
Thanks. Next question is from Anonymous. Does strong lensing really measure H0 or H of Z of the lens?
So, so what is actually constrained is the time delay distance. And the time delay distance has factors of 1 over H0 in it. The redshift dependent term is in there, but you can factor out the H0 piece. So it does really constrain H0. It is also weakly dependent on other factors like omega matter and omega lambda, but those are very weak dependencies. It's mostly sensitive to H0.
Next question is from Suhail Dawan. What is the impact of the omega m prior on the inferred value of H0 in lambda CDM / W CDM?
Yeah, so the omega matter is very weakly constrained. It's almost not constrained. So I'll just show you. So in this plot here, this is from Anwar's paper. This panel right here is showing the omega matter versus H0 contour, and you see the omega matter constraint, it's almost vertical, like there's almost no constraint. So it basically doesn't matter.
Next question is from Mikhail Rigo. How sensitive are you on the accuracy of your PSF modeling when reconstructing the lens profile?
I see. So it's a question about if the PSF was wrong, how wrong is our lens mass model?
Yes, I think so.
Yeah, I think, so we're actually doing some testing on that recently. So when I looked at this several years ago, there can be biases due to an incorrect PSF. So when you have a PSF that you know for sure is wrong, there can be some biases. I don't think it was huge. I think it was like the few percent level, so it's something you have to worry about. But what I didn't mention in my talk is we actually correct our PSF. We have an iterative correction method using the lens quasar images themselves that we use to reconstruct the PSF. And when you look at the residuals in our lenses, even at the quasar positions, they tend to be fairly good. So yeah, if the PSF was significantly wrong, it could create a bias, but we think we have a pretty good handle on the PSF correction.
Okay, thanks very much, Ken, for the talk and answering the questions, and also to the participants for asking the great questions. The time is up, so we'll have to move on to our next speaker. So our next speaker is Dominique Pescia, who will tell us about the Megamaser cosmology project.
All right, thanks, Sherry. Are you able to see my presentation over here?
Yep, can see. Thanks.
All right, great, thanks. Yeah, so I guess I'm going to start by echoing many other folks' thanks to all the organizers for pulling together this virtual conference. And today I'm going to be presenting on some of the latest results to come out of the Megamaser cosmology project, focusing in particular on our current Hubble constant constraints. I'd like to note that the Megamaser cosmology project is an international collaboration led by Jim Bratz at NRAO, and so I'm really just speaking here as a representative of this larger effort. All right, so I'd like to start by briefly reviewing what these Megamaser systems are and how we use them to measure distances and thereby to constrain H0. For this talk, I'll be focusing on masers that reside in AGN accretion disks, typically at radii of a few tenths of a parsec away from the central supermassive black hole. And it turns out that the physical conditions in these disks are capable of supporting a population inversion of a particular rotational transition of the water molecule, whose energy levels I've highlighted here in the diagram on the right. And because this transition emits at a frequency of about 22 gigahertz, we observe it in the radio. And it can be quite luminous, something like 1,000,000 times more so than the 22 gigahertz water masers in our own galaxy, which is why we use the prefix mega for these systems. And the first disk Megamaser system to be discovered was the one in the galaxy NGC 458, which has already come up a number of times in this conference. And there's really quite a nice story here about the history of our understanding of this system that I don't really have time to do justice to today. But basically, even though the system was first discovered in 1984, it wasn't until a decade or so later, with the advent of more wideband receiver systems and the construction of the VLBA, that it was really recognized just how interesting and unique and important this system would be. So here, what I'm doing is I'm showing the original 1984 spectrum compared with this more wideband 1993 spectrum that first captured the full extent of the maser features in the NGC 4258 system. The first VLBI maps were made shortly thereafter, and here I'm showing a modern version of such a map from Liz Humphrey's 2013 paper with the maser spots colored by velocity group. And then on the right here, I've plotted the rotation curve of these masers, showing the beautiful match with Keplerian motion that has enabled this system to be such a powerful tool. And the punchline here is that this accretion disk, as traced by the water masers, seems to be consistent with being both extremely thin and nearly edge-on, and that the gas in this system seems to be executing almost perfectly circular orbits within a point mass potential. So now I'm going to run quickly through the basic picture we have for disk masers more generally. So here's an example spectrum for one of the MCP maser targets, showing the characteristic triple-peaked spectral structure with two groups of high-velocity maser features displaced by several hundred to 1,000 kilometers per second to either side of the central group of features, which themselves coincide with the systemic velocity of the galaxy. And to set up some common vocabulary, I've just labeled these three sets of features and colored them accordingly. And I'm going to be using this same coloring scheme throughout the talk and referring to these three groups of maser features using this language. So here's a cartoon of one of these accretion disks, where we as the observers would be located towards the bottom of the screen because we would be seeing the disk edge on. But I'm showing it face on here so that we can more easily see the locations in the disk where the three groups of maser features are being emitted from. The red-shifted and blue-shifted features are emitted from what we refer to as the midline of the disk, which is where the disk plane intersects the sky plane. And the systemic features are emitted from the front side of the disk along our line of sight to the black hole. And these emission locations are largely set by the disk dynamics. Because maser amplification is a stimulated emission process, as the seed photons propagate towards us and pass by inverted molecules, they're only going to stimulate emission from those molecules if the photon frequency is within resonance. And this means that the stimulating photon can't be Doppler shifted by very much with respect to the molecules it passes, or else it won't stimulate that additional emission, in which case amplification won't occur and we won't see anything. And the takeaway from such a picture is that the strongest maser amplification we see should occur on lines of sight through the disk where the line of sight velocity gradient is very small. And for a material on circular orbits, this is going to occur where the line of sight is either tangent to or perpendicular to the orbiting material. And so we see groups of maser features in these particular locations, not because these are the only parts of the disk that are producing maser emission, presumably all or most of the disk is capable of doing so, but rather because these happen to be the regions where the amplification along our line of sight is maximized. And then on this slide here, I'm just showing the behavior of the acceleration vectors for the three groups of maser features, because it turns out that one of the relatively unique properties of these systems is that we're able to measure the line of sight accelerations. And we can hopefully see pretty easily from this diagram that we would expect to find generally positive acceleration measurements for the systemic features and essentially zero accelerations for the redshifted and blue shifted features. And in practice, this is of course what we see in the data. Getting a bit more quantitative now, I'm gonna walk through how we can use these maser measurements to get constraints on the distance to the system. Remember that we're seeing this disk edge on. So for a single maser spot, like the one shown in black here on the right, we only have access to its projected radius in the disk. And likewise, we're only able to access the line of sight components for both the velocity and for the acceleration, which for a point mass potential are related to the mass of the central black hole and to the orbital radius of the maser spot, as shown in these equations, with a factor of the distance to the system multiplied in to convert from angular to physical orbital radius. And here I've now circled the quantities that we measure directly in green, and I've circled those that we have to infer in red. And for a single maser spot, if we only had one maser spot that we were measuring in the disk, we can see that there's actually not enough information. There are 4 quantities we'd like to know, and only 3 measurements. But if we had a second maser spot, then the mass and the distance, m and d in these equations, are global properties of the system, right? They would be shared by both the first and the second maser spot, so they won't change if you have access to a second spot. The only additional parameters that you have to deal with are the orbital radius and azimuthal location of that second spot. And you'd get access to 3 additional measurements, the same 3 circled in green. So that would actually balance things out. You'd have 6 measurements and six additional things you'd like to know. And if you have more than 2 maser spots, the situation, of course, gets even better. So the maser disks we observe tend to have dozens to hundreds of maser spots. So the problem ends up being actually quite well posed, and unique solutions exist for both the black hole mass and the distance to the system. Of course, in practice, we are a bit more sophisticated in our modeling than the simple picture I outlined in the previous slide. We relax a number of the idealizing assumptions, but the aspect I'd really like to focus on here relates to some work we've done recently on improving our handling of the systematic uncertainties in the maser spot position, velocity, and acceleration measurements. We are now incorporating these systematic uncertainties into the modeling itself as free parameters, allowing us to derive them from the data directly. And in doing so, we found that previous efforts were actually typically being too conservative in many cases, and that this new method results in improved uncertainties for many of our quantities of interest. And I'm showing here the evolution of the distance measurement for NGC 4258 from the literature. And the latest measurement from the Reed et al. Paper is shown in red. And the Reed et al. Paper used this new approach for handling systematic uncertainties, which ended up resulting in a factor of about 2 improvement in precision over the previous measurement by Humphreys et al., even though both papers used the same data. And pretty much all of that improvement comes from a decreased systematic contribution to the uncertainty. The total uncertainty ends up, for the distance to this galaxy, ends up being about 1.5%, which is the current state of the art. But all right, moving on really to the main theme of this conference, which is of course the cosmological application of this technique. and in particular, the recent results from the Megamaser cosmology project. The Megamaser technique is geometrical and provides both the distance to the galaxy and a measure of its recession velocity in a single step. So in principle, we obtain a constraint on the Hubble constant using just one galaxy. But in practice, the precision is complicated by the fact that these systems are pretty rare, and most of them are considerably farther away than NGC 4258 is. Here I'm showing the relative physical sizes of the different maser disks that we've targeted in the MCP, and I'm comparing them to the size of the maser disk in NGC 4258. And it turns out that they're all really quite comparable in actual size, which is itself interesting and is probably telling us something about how, where, and when these systems form in the AGN life cycle. But of course, what we see on the sky is the angular size of the disk. And because the MCP targets are so much more distant than NGC 4258, they're both much fainter and they subtend much smaller angles on the sky, to the point of being comparable in size to our VLBI beam. And these observational limitations currently prevent us from achieving a 1.5% distance measurement for these other galaxies, like we do for NGC 4258. And instead, the goal of the MCP has been to combine the distance measurements from multiple galaxies to achieve a more precise constraint on H0. And to date, we've published distances to 5 Megamaser hosting galaxies in the Hubble flow, each of which is the end product of dozens of hours of telescope time and typically 1 to 3 years of downstream data reduction and analysis. And most recently, we've published a paper combining the results from these 5 MCP galaxies with the NGC 4258 measurement to derive a maser-only Hubble constant constraint. Under certain assumptions about the impact of peculiar velocities, which I'll touch on more in just a moment, we find a value for H0 of 73.9 plus or minus 3 kilometers per second per megaparsec. Our corresponding Hubble diagram is shown here on the right, and I find it quite illustrative because even without the overplotted line here, which is the best fit, the story in this plot is pretty clear. And furthermore, I think this plot also nicely addresses a point that came up in one of the panel discussions earlier this week, this notion that there's only one useful maser galaxy, namely NGC 4258, because what we have here is a set of 6 independent measurements that require no calibration, that really seem to corroborate one another, and that fall on a single and reasonably well-constrained line in a Hubble diagram with good fit statistics. So this is not a one galaxy show, and I hope these results can help to do away with that perception. But all right, on to the sources of uncertainty in our constraint. And the primary source of systematic uncertainty in our H0 constraint comes from the unknown peculiar motions for each of the galaxies. And I was very happy to hear Tamara's talk on this topic earlier today, because we really agonized over these quite a bit when writing this paper. Because the MCP targets all have recession velocities on the order of several thousand to a bit over 10,000 kilometers per second, they're all reasonably close in the grand scheme of things. The peculiar velocities can constitute a few % of the overall velocity. And because our sample size isn't huge, these won't necessarily all average out super nicely like we would expect to happen in a much larger sample. So we've explored a variety of different possible ways of handling the peculiar velocities during the H0 fitting process. And these are shown in perhaps gory detail here on this slide. We tried adding a constant uncertainty to all measurements. We tried modeling the peculiar velocity distribution during the fitting process itself and drawing from it for the individual galaxies. And we also tried correcting each galaxy's motion using galaxy flow catalogs or correcting to group motions. And overall, we found that the H0 values determined by the different peculiar velocity treatments span a range that falls within 1 sigma of our fiducial maser-only value. And so we decided to present these different treatments as being essentially different models. So each of them is reported here, each of them is reported in the paper. And if you have a preferred method for correcting peculiar motions, hopefully we've represented it among these. The primary source of statistical uncertainty in our H0 constraint, and in fact still the dominant source of uncertainty overall, comes from the quality of the individual distance measurements, which are typically about 10%. The contributions to this uncertainty for any single galaxy tend to be specific to that galaxy. But one common issue we run into is in measuring accelerations for low signal-to-noise and spectrally blended maser features. When we have these monitoring spectra, and you have a lot of blended maser features trying to discern the acceleration of any one of them, we model them all jointly, but becomes very difficult, and you end up having a large uncertainty in that, which tracks through to the distance measurement. And mitigating these issues is really quite tricky because they're largely signal-to-noise driven, and we're already regularly pushing the sensitivity limit for current radio facilities. But next generation facilities, and in particular, I'm calling out here the NGVLA, will enable much more sensitive mapping and spectral monitoring of these maser systems and correspondingly better measurements. And of course, probably the biggest limitation for the MCP measurement at the moment comes from the small sample size of only half a dozen sources that we're using to constrain H0, which opens it up to shot noise and gives us limited statistical resources for beating down the individual measurement uncertainties. We've assessed the degree to which individual galaxies influence the overall measurement using leave one out jackknife tests, which indicate that none of the galaxies are overtly tugging the H0 value one way or another. And we do have a few more galaxies in the works right now that are undergoing analysis and will be published at a later date. But to my mind, the most promising avenue towards mitigating all of the uncertainties I've mentioned so far is really just to substantially increase our sample size. And there are a number of avenues to pursue on that front. I've listed some of them here. Next generation facilities will of course be great, but in the meantime, there are ongoing efforts to improve the currently rather dismal efficiency of Megamaser surveys at 22 gigahertz, as well as to identify suitable alternative maser transitions that primarily fall in the millimeter and sub-millimeter waveband, and which can be used in an analogous manner to what's been done at 22 gigahertz as tools for measuring black hole masses and distances to objects, and may open up either independent measurements of the objects that we've already measured or are capable of measuring at 22 gigahertz, and thereby increasing the precision of the measurements for those objects, but also potentially open up entirely new objects to study. And this is work that's ongoing at the moment. And with that, I'll just leave my summary slides up here, and I will take any questions. Thank you.
Thank you, Dominique. We have several questions on Slido. First one is from Dragan Hutter. How is the distance to NGC 57 law so accurately determined when it's at Z much greater than that of NGC 4258?
So I assume this is NGC 5765b that's being referred to here. Yeah, so NGC 5765b is one of our best systems. It's a bright system compared to most of the others. It has very strong systemic maser features, which is that central group, and it has very broad high velocity. So it has a very broad velocity range covered by the high velocity features. So the brightness obviously just increases and improves our signal to noise. The broad velocity spans of the high velocity features allow us to really nail down the dynamic center. And it turns out that the accelerations, the systemic features have reasonably well separated masers spectrally that we're able to track the accelerations very well. And so just the quality of the measurements for that system is just a very well-behaved system in a number of ways. And the quality ends up being quite high. And so we get really quite a good measurement for that one. It's still a factor of several less precise than NGC 4258. So I'm not claiming that it's comparable, but it is the best of the MCP sample.
Next question is from Tom Shanks. George Efthasu claims a 3.5 sigma difference between the three geometric distances to NGC 4258. Any comment?
The three geometric distances. So this means the maser distance, the Cepheid distance, and some third, maybe tip of the red giant branch or Myra's or something. I'm not familiar with this discrepancy. I don't have any comments on it.
Next question is from Wendy. So earlier in the conference, you commented that about megamasers was that there was just a single 0-point calibrator, NGC 4258. There are no other systems nearby. That fact remains, is that correct?
I think, I don't know out to what distance the Cepheid calibration can be done, but I believe that does remain correct. I think the closest system other than NGC 4258 is UGC 3789, which lives at about a 50 megaparsec distance. And I think the Cepheids peter out at something like 25 or 30. So I believe that's right.
Next question is anonymous. How large are the systematic uncertainties involved in reducing the measurements to the CMB frame velocity? Are they accounted for in the fit?
I just want to repeat that. Could you repeat that question again?
Sure. How large are the systematic uncertainties involved in reducing the measurements to the CMB frame velocity? Are they accounted for in the fit?
Yeah, so the measurements of the velocities of the galaxies we have they come directly from the Maser modeling. So they're precise to of order a kilometer per second. So it's a part in 10 to the 5 or so in Redshift. So that's really small. And then converting those velocities to the CMB frame really just depends on their location in the sky and our knowledge of how quickly we're moving with respect to the CMB. So I don't think that conversion has really any uncertainty associated with it as far as we're concerned.
Next question is also anonymous. Presumably, peculiar velocity correction affects the H0 from nearby masers. Is there any particular maser whose peculiar velocity drive the difference in H0?
Right. So absolutely, the peculiar velocities affect the H0 value that we derive in the manner that I presented, and our tests to try and pull out different galaxies from the sample and refit the entire thing, these jackknife tests I referred to, indicate that no, there isn't any single galaxy that's tugging it by a sizable fraction of the quoted uncertainty in either direction. And in fact, there seem to be comparable tugs in either direction. If you remove one galaxy, it moves it up. If you move another galaxy, it moves it down by similar amounts. So I don't think there's any one sort of overly influential galaxy in our sample.
Next question is also anonymous. How many sources do you plan to incorporate, and within which reasonable time period to improve H0 value from masers?
So in the near term, for the Megamaser cosmology project, we do have, like I said, a handful of other sources that are currently undergoing analysis. Data has been taken, and we're working on reducing those data and analyzing them. These are sort of time-intensive measurements. So I would say that at the end of it all, we may have as many as twice as many sources as we currently have, maybe slightly fewer, maybe 10 or 11 total sources from the Megamaser cosmology project that we're hoping to use to push this uncertainty down from currently about 4%, maybe as much as another percent or so. That would be great. The longer term prospects, I think the Megamaser cosmology project, as named, will come to a close at some point, and then we'd have to look towards a sort of second phase of this project that really folds in the capabilities of the instruments and facilities being built right now, which could be substantially more expansive. And I haven't really gotten into that here, but there are certainly ideas for what we could do in the future.
Okay, so I think given the time, we will have to move on, but let's thank Dom again. Our next speaker is Bernard Schutz, who will tell us about standard sirens.
So do you see my?
Yes, we do. Thank you.
Great. I'm getting a lot of feedback. Maybe I'll do something. Yeah, that's better. I'm very pleased to be here and to be able to present at this very interesting meeting and seeing all the progress that's being made on measuring H0. I want to update you on what's happened with the standard sirens measurements of H0 that we started making with GW 170817, and we're continuing to work on. We took our first baby step with that wonderful event that occurred remarkably closely to our position in the universe, and which we were able to localize very well on the sky and very quickly get an identification. Using that identification and just the gravitational wave data that we had, we were able to estimate the distance, and I'm going to talk later about how that works with gravitational waves. And from the distance and then the corrections for a peculiar velocity to get our value of the Hubble flow at that position, we published these two graphs. The first one, the one on the left, is the posterior distribution for H0. Very nicely falls in between Planck and Schu's. However, it's got a very broad tail, and the part of the reason for that broad tail is in the diagram on the right, which is a plot which vertically shows the inclination angle of the system, of the binary system, and horizontally is the Hubble constant. And you see that there's a correlation between estimating the inclination angle and estimating the Hubble constant. That correlation comes from a correlation between inclination angle and the distance estimate, and that prevents us having the small error bars on that one event. We got the distance. We estimated. We published after reanalyzing the data in 2019. Our best value for H0 from these data is 69 with fairly large error bars, plus 22 minus 8. And I will always be quoting numbers which are the mode with 68% range either side. If we went to the median, that would, as you can see from the shape of the graph, that would push us up closer to Schu's, but we're consistently using the mode as the numbers that we're quoting. The problem was not that the signal was weak. It was the strongest one we've had so far. The problem was that the degeneracy I talked about between inclination and distance weakened the error bars, and also, as we've heard, that the velocity estimation is difficult. So what's happened since then? Well, we've had data from estimating the inclination angle from the jets. I'll quote particularly the superluminal motion. This paper in 2019, which gave a value not very different from ours, 70.3, but with markedly reduced errors. And that it depends upon a reasonably good measurement of the inclination that comes from the jet superluminal. We've also started using dark sirens where there's no counterpart. These are usually black hole mergers, and what you try to do is use a statistical method by which you associate the merger with a number of different galaxies in the field of view in the error box that's given from the detection. and then use one of a number of methods to try to get a value. If you have only one dark siren, then all you can do is average over all of those possible values. And but if you have a few, and if I come down to the fourth point, we took 4 black hole coalescences from observing runs 01 and 02, along with the original one. And there you can cross-correlate the possible values you get from the error boxes of each different detection, and that allows you to home in on the values that keep repeating, that are stronger. And that came out with 68, but again, fairly large error bars, plus 14, minus 7. Yesterday, the collaboration just announced their analysis of GW 190814, which is a very interesting merger in itself, with a massive black hole, 23 solar masses, and a compact object of 2.6 solar masses, which might be a heavy neutron star, might be the lightest black hole that has so far been identified. So that's interesting in itself, but we were able also to use that as a dark siren and get another value that's given in that paper that was released yesterday, 70, with fairly large error bars. So that's where the collaboration is so far. I want to describe what standard sirens are. The gravitational waves, it comes back to fundamental issues in general relativity. The gravitational waves, of course, are a coherent emission from the system. So we not only get amplitude and intensity, we get amplitude, we get the phase. And most of the information we deduce comes from the phase, tracking the orbital evolution through the phase of the gravitational wave. General relativity is scale-free. Unlike electromagnetism, there's no such thing as electric charge, and that means that everything scales with m. Now, the luminosity, on the other hand, is dimensionless if you set c equals g equals 1, and that means that in scaling, it will not depend upon m. And that means that, for example, a merger of 2 small black holes or 2 large black holes will have the same luminosity in gravitational waves at the very end of the merger. The difference in the energy emitted is that the larger black holes will take a longer time. That time does scale with them, and so they'll be at that luminosity for a longer time. What is the measure of the luminosity? It has to be a dimensionless number, and that dimensionless number, one way of expressing it, is the number of orbits that remain before the merger, at least in the point particle approximation when the objects are fairly far apart. And you can measure that, you can compute that if you just measure the frequency and the rate of change of the frequency. You're watching the orbit evolve, and you can calculate from that the number of orbits remaining in there for the luminosity. And that's why we have a standard luminosity from a binary system at any stage of its evolution. That would be very nice, but binaries radiate anisotropically, and that means that the radiation is stronger coming up perpendicular to the plane of the orbit than it is in the plane. There's a factor of 2 there. And if you don't know the inclination of the orbit, then you're going to have an uncertainty of that factor of 2 in the distance you infer, because you don't know exactly what the luminosity is going to be. Or you don't know exactly what how to convert the amplitude into luminosity. So that's why the inclination and the distance are correlated. Now, there's devils in the details, of course, and the problems that we have, some of the previous speakers have mentioned some of them. The first one, of course, is if we don't have enough detectors, we're not going to get the information. To get the inclination, we have to measure the polarization of the gravitational wave, because that depends, if you're looking face on, it's circular. If you're looking edge on to the system, it's linear. So the polarization tells us what the inclination is, but we need, if we have no other information, we need at least 3 detectors to measure the polarization. If we have a counterpart in the sky, we need 2. With GW 170817, we had two detectors. Virgo did not have much of a signal, but we had the two LIGO detectors, but unfortunately, they're quite closely aligned and they don't resolve polarization very well. And that's why we had a polarization problem, an inclination problem. Another possible problem, and this is a serious one they're giving a lot of attention to, is calibration, the detector calibration. You have to convert the output that you see in volts in the interferometer to the displacements of the mirrors. And to calibrate that, you have to move the mirrors physically over very, very tiny distances with very weak perturbing forces that you actually understand and that you can actually calculate. So our calibration at the moment is better than 5%, and we're expecting that we can push it to about 1%. And we have new methods under development to go below 1%. But that sets a floor because it's probably got a large component of the error in calibration will be correlated between detectors if they're using the same methods, and so on. So it won't be a pure statistical error. So we have to look at the calibration as a kind of floor at the moment on the errors that we're going to get for distances. Then another problem that we have is determining the inclination. As I said, it depends upon the polarization, but the problem with this is that there's a bias. Our selection bias is that we're going to see preferentially systems that are face-on, and that's a maximum of the intensity of both polarizations. So as the system tilts away from face-on, you're moving away from a maximum, and the polarization resolution, therefore, isn't well measured. So we might have signal noise very high. We might have, for GW 170817, we had errors around 2 to 3% in the measurement of the amplitudes of the gravitational waves, but that translates into 15 or 16% errors in the inclination. And a final source of error that we will have is in weak lensing. That's not an issue right now, but it will be for LISA. That might come in at the 1% level for LISA. These errors are random and unbiased, apart from calibration. The inclination error, in particular, you can compensate for in a Bayesian way by taking appropriate priors. So what they do is that they make it difficult to use some of the systems and reduce the number of systems that you are actually using. The systematic errors in calibration, when we get to the LISA mission, won't be a problem because LISA is self-calibrating itself. Well, Wendy Friedman mentioned in her slide about all the different methods that the most difficult one for this method is the event numbers. And so I want to talk about that. The analysis is now going on for the events that we have in O3. Again, they're dark sirens mostly. I don't expect it to change, make a dramatic improvement in what we are on the numbers we're quoting. But O4, when it starts up, we're in the upgrade right now, or when we get back into the after we're allowed back into the systems, we're going to be upgrading the sensitivity again, and then will come O4 with an event rate something like 10 times higher than they have been up till now. It might be that we'll have enough dark sirens that will get a markedly improved errors on H0. It might be that we'll be lucky and we'll get a number of bright sirens from binary neutron stars. The problem with bright sirens has been identification of them. The ones that we've had in O2 were too far away to find a positive identification. The Vera Rubin Observatory might change that. It might give us a database where we can find the kilonova events. With the dark sirens, we have to associate them with galaxies at the appropriate distance, and we use galaxy catalogs, and those catalogs are not terribly complete at the distances we go to. There have been a number of studies about what we can do with 5 years at full advanced LIGO sensitivity. That would be starting in another couple of years. And we can probably get to 2 or 3%, both with bright sirens and with dark sirens. But it does depend upon being able to capture those kilonova events and being able to use catalogs that have, where more of the galaxies are cataloged and have redshifts that we can use. I want to mention that LIGO will be upgrading. Even when it reaches advanced LIGO, that's not the end of the road. It's already funded, and the technology is being developed between America and Europe to upgrade the sensitivity by another factor of 2 or so, called LIGO A+. That's going to make a remarkable difference to this argument, actually, because when we get to A+, there'll be a significant number of events, dark siren or bright siren, where we'll be able to finally measure higher harmonics in the radiated wave, not just the quadrupole radiation. The interesting thing about that is they have different radiation patterns. So if we can nail some of these harmonics, and we did actually in the paper that came out yesterday for the first time, but if we can nail some of those harmonics, then they give us a higher precision on inclination. They break the inclination distance degeneracy, and they also give us better sky location. And there'll be quite a number. It's expected to be quite a number in the A+ regime of dark sirens, which we can localize to a single galaxy, even without an identification. And that will change the game completely. And I don't want to leave this slide without mentioning that how important it is to our science that when we make these announcements of gravitational wave candidate detections, there are so many groups that go out and try to find the counterparts. We really appreciate that effort. In the longer term, I'll just mention LISA launching around 2034. Some of the binary black holes will have incredible signal to noise and will be calibrated at those signal to noise, but there'll be some systematics from weak lensing. And so it remains yet to be seen how we're going to solve that and what the accuracy which we can get to in the face of that. But working with Athena, which is planned to fly at an overlapping time, we may well be able to identify individual galaxies in which the supermassive black holes mergers have happened, and that will again be not just great for Hubble constant, but with the sensitivity that we have, we may well be exploring dark energy. A bit later than LISA, we would expect third generation ground-based detectors to be operating, like ET in Europe and Cosmic Explorer in the USA. Their sensitivity is such that they'll see every binary neutron star, every binary black hole system in the appropriate mass range anyway for the black holes that happen, any merger that happens anywhere in the universe. And so we'll be, many of them will be observed at signal noise of 1,000 or so. And so again, there may be some weak lensing problems, but the uncertainties for H0 may well be down around 0.1% at that point. But that's something that we're talking about, which is a good 15 years away. So I'll just finish with the slide which compares the LISA and ET sensitivities. Vertical scale is Redshift, out to Redshift 20, and the coloring is the signal noise ratio, which they can observe binaries with masses along the horizontal scale. And you can see that they'll be detecting these binary black holes everywhere. So that's the end of my talk. I'll pause there and take questions.
Thank you. Thank you, Bernard. I have several questions. First one from Dan Skolnick. What is the current best estimate after this last year of observation of the rate of binary neutron star mergers?
I don't know the, I couldn't answer that, but I would refer you to the paper that came out yesterday, because there's been a reevaluation of it. I just don't have the number off the top of my head.
Next questions from Matthew Colles. How many dark sirens are needed to reduce the H0 uncertainty to 1% using that method?
We think we can get to 2 or 3% with about, for dark sirens, with about 250. That, however, depends very much upon the completeness of catalog. So when I say 250, that's where there's a reasonably small number, maybe a few thousand candidate galaxies in a field of view. Right now, we're working with error boxes which have tens of thousands of galaxies. And when you're trying to cross-correlate over there, you're always going to get a lot of false positives. So we think with about 250, we can get down to 2%, 1%. Well, probably the answer to that is that the increases in sensitivity of the detectors, before we get past 250, we'll be into the A+ era, and we'll have more sensitivity, and the accuracies will improve just because of that.
Next question is again from Matthew Colles. Surprising that after 5 years, bright and dark sirens give comparable H0 precision. Could you explain why that is?
It's because of this astounding circumstance that we have so many more dark siren detections. I don't think anybody going into this expected that we'd be detecting so many black hole mergers at significant distances, but with quite strong signals, that the masses are higher than we expected, and so on. So it's just in the numbers.
Next question is anonymous. Did you account for peculiar velocities in determining H0 for these nearby galaxies?
We've already had some discussion here at this meeting of the peculiar velocity problem Tamara talked about for the first detection. The ones that are further away, the peculiar velocities don't matter so much, and all of the systems that we've been talking about and using in these papers that I referred to are at least 150 megaparsecs, and some of them 300, 400 megaparsecs away. At those distances, the peculiar velocities don't make a difference at the level of the uncertainties that we're quoting.
Next question is also anonymous. Has COVID disrupted the planned observing runs on LIGO?
Yeah, we finished, I think it was the 26th of March. We shut down early. We had expected to go a couple of months longer. The plan now is of course to install the next grade of technology improvements to get to the next step for 04. And work at the observatories is slow because we have to be careful about COVID and all the restrictions in the different states, the different rules that they have on what can be done at the moment.
One last question from me. For the bright sirens, how long would the electromagnetic counterpart last in duration?
We it depends, of course, on how far away it is, because it fades below a detection limit. But judging from the kilonova that we saw in 1708-17, if you put that out at 150 megaparsecs, you probably have to catch it in the first day or two.
First day or two? You
Day,
said?
day or two, yeah.
Oh, okay. Wow. That might be tough.
But again, it's long lasting in, and that of course assumes we don't get a direct hit from the gamma rays and so on. But it's very long lasting in the radio. But again, you need very, very high sensitivity. And it could be that with SKA, we'll be able to find some of the radio signals much later than that, because they develop after the jet emerges and so on.
Okay. Thank you, Bernard. And now we're moving on to the panel discussion. So I will share a screen. And can I ask the speakers and the panel members to turn on their video, please? All right. Can people see my screen? Okay, so today for this afternoon's panel discussion, we have our 4 speakers of today. So Tamara, Dominique, Bernard, and Ken. And as panelists, we have Richard, our chair of the organizing committee, Simon Beer, Ofer Lahav, and myself. And we have put together a list of discussion topics that we could go through during the next 30 minutes. So first is how to handle peculiar velocities, how to increase the sample of lenses or masers and sirens, what are the required follow-up observations to mitigate systematics, what do we learn about type 1a supernova from lenses, masers, and sirens, what are the prospects of bright sirens versus dark sirens, and how do the H0 measurements depend on redshifts or cosmology. So we'll go through these points and also some additional points from the Slido that we didn't get into. So for the first point, how to handle peculiar velocities, maybe Ofer, would you like to say something first? You're muted. Can you unmute?
Thank you. Yeah, so thanks, Jerry, and thanks to the organizers for a great meeting, very stimulating. And the peculiar velocities were already mentioned, actually more than I expected. So it's clearly becoming very topical again. I can recognize people on the line who spent a good deal of their career on peculiar velocities. This was the, a very important topic, a major probe of cosmology, some, let's say, 30 years ago. So it's interesting, it's coming back through the back door to probe. Should also mention peculiar velocities, we should not just look at them as nuisance. They're actually extremely useful because they are, in fact, the only probe of dark matter on large scales locally, alongside, of course, weak lensing at high redshifts. So this is just a general comment. Can you hear me?
Yes, we can.
Hello?
Yes.
It's frozen.
We're here.
I can hear you, Sherry. Yeah, and Ofer.
You can, okay, you can hear both of us? Okay, yeah. Guess one question I had, yeah, I think Ofer is frozen. The one question I had about the peculiar velocity reconstruction. So in Dominique's work, for example, he went through the various different models. How would like new survey data in the future or spectroscopic data allow you to better reconstruct these flows, bulk flows and peculiar motion velocities?
Yeah, so for the work that I mentioned, we really pulled from other people's work on the flows, right? We did not attempt to do any large scale flow modeling of our own. So we pulled from the cosmic flows work, Cosmic Flows 3. We pulled from the 2MASS++1.
Yeah.
Welcome back, Ofer.
I'm sorry about that, somehow, technology. Sorry, please carry on.
Oh, no worries. I was just addressing Sherry's question. So I don't have a great sense of how limited those are right now, spectroscopically or anything like that. I think, yeah, it would be nice from our end. Consistency between the catalogs was something we were worried about quite a bit. It wasn't clear often what the uncertainties in the local motions at any given sky location and redshift sort of were from a lot of these things. So for anybody on the line from that area of work, it would be if there's a way to sort of associate a certainty with the magnitude and direction of the flows in any particular region in these catalogs, that would be at least helpful for the Maser work.
Yeah, some things that could really help. You go ahead, Ofer.
Sorry, I just wanted to kind of highlight on peculiar velocities, which were very nicely presented by Tamara, that an important issue is the smoothing scale. It came up in question. So the point is, what is a peculiar velocity at a point in space? Well, such a thing is not that well defined, actually, and normally one has to average over a certain volume or over a certain number of galaxies. So could you hear me?
I'm able to hear you.
Yeah, okay, good. So the point is that, for example, if we're talking about W17, 817, peculiar velocity for NGC 49993 has not been measured for whatever reason. So what the original LIGO-Virgo paper has done, the Nature paper, they averaged members within 8 megaparsecs. But of course, that is somewhat ad hoc, right? You can change the smoothing scale and get different values. In parallel with the Howlett and Davis paper, there was also a paper by Mukherjee and also a paper by our group led by my student, Konstantin Nicolaou. And what we've done there,
Oops.
May have lost
We
Ofer
lost Ofer again. Okay, but Tamara, you wanted to say something, so.
Yeah, well, it's true. I was actually remiss in not mentioning his papers as well when I was talking about that, because there's been a few different versions of the reanalysis with the peculiar velocities. I was just going to point out that when you're looking at peculiar velocities, there's sort of a few different major ways of measuring them. You can take there's only a very limited number of galaxies where we actually have direct peculiar velocity measurements of them, which includes supernova hosts, Tully-Fisher fundamental plane velocities. And then you can make create a velocity field from a density map if you've got a really good measurement of the densities, or you can create a map based on the combined measurements of velocities. So you asked what could we do to improve the data and the peculiar velocity reconstructions. A lot of the peculiar velocities come from very large modes. So it's like very large structures that cause the peculiar velocities. And the current redshift surveys aren't complete out to big enough redshifts to be able to capture the large modes. And so by having a much more complete redshift catalog to higher redshifts well beyond the velocities that we want to measure, that would be one way to get much improved estimates of peculiar velocities for objects that we haven't measured their peculiar velocity directly in particular.
Perhaps
And to add to this, Tamara, another possibility is to use galaxy redshift survey to reconstruct velocities. Right?
Yep, that was
And
actually what
that's-
I was referring to. Yeah.
Right. Okay. So there are two ways: the actual Dean sigma Tally Fisher and the redshift survey, which depends on biasing. That's right.
Perhaps this would be a good time to include a question from Saurabh Jha that he had mentioned on Slido, which is, do you find any systematic differences between galaxy optical and radio H1 redshifts? Radio Zs listed in catalogs are extremely precise, but are they accurate?
That's actually a project I'm working on at the moment with a student. We're looking at that, but we don't have an answer yet.
Okay, so then moving on to our next discussion point on how to increase the sample of objects. So masers, lenses, sirens. We've heard from our speakers today, some prospects already. Maybe we can dig a bit more about some more concrete numbers. So Dominique, would you like to start?
Sure. Yeah. So I think I'll tackle the masers aspect of this. I'm sure Ken or Simon or you would have more to say about the lenses, and I think Bernard gave already a pretty nice overview of how to increase the sample size of the sirens. For the masers, the MCP survey component, where we looked at several thousand AGN for these 22 gigahertz water masers residing in the accretion disks, is complete at the moment. By which I mean it's done. It's not complete in a volumetric or something sense. It's finished. The survey component has wrapped up, and so I think the next phase of searching for these sorts of systems, short of waiting for new facilities to come online with the corresponding increased sensitivity and depth of volume that will entail, requires being thinking a little differently. And I sort of briefly mentioned these at the end of my talk. For the 22 gigahertz systems, our surveys so far have been very inefficient, on the order of 1% or 2, or maybe a few percent detection rates, and largely non-detections. If we could be if we knew a little bit more about the environments that these systems lived in and the sorts of AGN we could be targeting in these surveys, really substantially improve our detection rate. There's quite a bit of work being done on this front, led by people like Anka Constantine and Cheng Yu Kuo, about improving the efficiency of these surveys. So that's where the 22 gigahertz stuff, I think, will live in the short term until the next generation facilities open up a sensitivity space. But the other avenue that I referred to are these millimeter and sub-millimeter water masers, right? So the 22 gigahertz transition is only one of an entire zoo of transitions that the water molecule has, right? And some of these other transitions can also be excited, can also sustain a population inversion in physical conditions similar to those that sustain 22 gigahertz transition inversions. And we've already started seeing examples of some of these systems since ALMA has come online a few years ago and is capable of really observing sensitively in this waveband. We've already seen some of these at 183 gigahertz, at 321 gigahertz, at a number of different frequencies. We've seen these water maser transitions in AGN. And so this is really a field that's just opening up. And I'm very hopeful that with surveys of these other transitions, and with the capabilities of a VLBI array like the Event Horizon Telescope, which can actually do VLBI at millimeter wavelengths, combining these sorts of facilities in the coming years, I think is potentially a way to open up the sample size for the masers, potentially substantially.
Thanks.
Perhaps related to this. Sherry, can you? Thanks. Perhaps related to this, are you, in your maser search, are you doing a specific search also for masers in galaxies that host stellar standard candles?
Right, yeah, so this question came up on Slido. I posted a brief comment to it in the Slack, but the MCP survey did not do such a specific targeted search. It was much more broad spectrum. But I know the short answer to your question is not that I know of. But many of the nearest AGN, right, the ones that would be useful for calibrating standard candles within a couple tens of megaparsecs, have just naturally been searched already as part of these other more expansive surveys. I don't know that that's exhaustive, and I don't know that there's a specific survey targeting standard candle calibration sources. But I would be surprised if there's a large number left of these stones left unturned at 22 gigahertz, just because they're mostly so nearby compared to most of the systems in our sample.
And speaking on the lenses, I would make two races here. One is the square root n race. So there we are approaching 2%. And so you increase the number of lenses. We expect of order 40 to 100 bright quasars that where we can get optical monitors, getting accurate time delay measurements and do all this analysis. So there we're on a good path, and particularly with upcoming optical and near infrared surveys, Rubin Observatory, LSST, Euclid, and the future is really bright on that side. And the other race in parallel is the systematics. And there the question is, what type of information do we require to pinpoint down major systematics that would avoid us to continue the square root n race down to the 1% level? And there in particular for me, and this is the Slido question that is on top that hasn't been asked yet, is what are the dominant systematics? And here I can speak for me, and this is mainly with mass profile assumptions or what's in there that we may or may not have probed. And there the key non-lensing observable that we have in discriminating different mass profiles or mass distribution effectively of this massive elliptical galaxies is kinematic observation. So stellar orbits of the massive elliptical galaxies. And in particular, what is very another systematics in there is anisotropy distribution in stellar orbits. So it's this entire other field. And what really helps is spatially resolved high signal to noise kinematic spectra of these galaxies. And so this can be a sample of dozens of MUSE observations that we're hoping or pursuing in the near future. JWST will be amazing on this. Will be limited to few lenses that we help to get inside and put it. So these are the two paths that I identify. And also, it's not just that we need this or can use this information from the actual quasar lenses. So there are tens of thousands of lenses on the sky, and they will be discovered with Euclid, with LSST, that will pop up, even like now with DES, Dark Energy Survey, with HSC, of these wide imaging surveys. We find hundreds of these lenses. And all of those provide information about massive elliptical galaxies and their profile. And so it's about how can we incorporate all this information.
Just one additional thing on the lenses discovered from these surveys. Yeah, we're discovering a lot now with like DES and HSC, and of course in the future with LSST and Euclid. There is a bit of a question as to how we've already discovered a lot of the bright, very useful lenses, and a lot of the ones we'll discover in the future will tend to be maybe fainter, smaller separation, maybe the time delay, the relative time delay uncertainty might be larger. So there is sort of a question of, do we try to go for all of them, or do we pick out some of the special ones that we think are going to be particularly useful, like the so-called golden lenses? That's another potential strategy, although then you have to worry about, are we creating a bias by picking those lenses? That's just something to think about.
Yeah, one thing I want to mention here is we are in a process of finishing a paper, which is still blind, so I cannot even know the answer to give. That is a first attempt or the first path where we dramatically lacks assumption on the models that we use by effectively introducing an additional mass sheet transform hierarchically or basically covariant over the entire sample of lenses that we have. So this is a very minimal assumptions of what we expect to know from lenses, and then use the kinematics that we currently have to inform the lens models. And then on the next step, we mitigate the uncertainties that eventually in just that procedure is inflating by adding a sample of 33 lenses from the SLAC survey, which both have HSD imaging and kinematics. Some of them even IFU with VMOS to be self-consistently folded into the analysis. And that's the current ongoing projects. And so stay tuned, it will come up soon, yeah.
Yeah, so just to add, I think, yeah, from the lensing side, we will have the many lenses, both lens quasars, lens galaxies, as Simon and Ken mentioned. I think it's more to prioritize the follow-up then, because we just don't have the observational resources to follow up them all. So then we would have to pick a sample, the easy ones to follow up. And then the main work is to make sure that any selection effect in this subsample is actually incorporated into the analysis. So following up on the resources required for follow-up, do any other panel members want to discuss about what resources is needed for follow-ups?
This could be a good opportunity for a question from Slido, which I think is related to this. The question is from Anonymous, and it says, if you need 30 to 40 lens systems to monitor each one of them for about 10 years to get 1% precision. So, you know, as you're building these samples, do you always need 10 years worth of data, or does this happen faster?
So right now, Cosmograil is in the process of monitoring of order 10 lenses. So some are already in the pipeline. In principle, you don't necessarily need 10 years, but you do need, at least with the traditional method, multiple observing seasons to overcome microlensing. So that's the big contaminant. I did mention this high cadence monitoring. I think there was a question on Slido about this also. But there was this paper by Fred Corban, 2018, doing a proof of concept. So instead of taking an image every few nights, we took an image every single night looking for smaller variations in the brightness of the lens quasar images than Cosmograil typically does. And the results from that initial pilot study were very promising. So if that becomes a thing in the future, maybe in one single season, just observing every night, looking for these smaller variations, it'll become possible to do it in one season.
Yeah, recently Marta Milan has a paper out on the archive where there's new time delays being measured from basically 1 to 2 seasons with a 2.2 meter class telescope. So this high cadence monitoring is working. So you actually don't need to monitor for 10 years. Thankfully, you can do it now in 1 or 2 per lens.
Could I come in on lensing with gravitational waves? We're waiting for our first lensed binary coalescence event, which will come at some point. And the great thing about that is it's a transient event. And so we'll have the time delay. We may have to wait 6 months or a year or something. There may be that long an interval between things, but the time delay will be measured to incredible precision, to seconds or less than seconds. And so I wonder if lensing people could say what then would be the limit on using that for H0.
So one limit for me is the location. So we need incredibly accurate and precise location within where the images appear. So if you're off by a few milliarc seconds, you may be off by a day in relative predicted time delay. And so in that sense, whether you measure something to a second or a millisecond, that I'm sure LIGO Virgo is capable, that is so below anything in the noise of our current measurements. So I would hope that you find one that has also luminous companion, and then it would be like, but I might be a bit too optimistic on that.
Okay, we'll try.
maybe I would like to ask a follow-up question based on that. So there was this beautiful system Refstal where you had the magnified and lensed supernova, and I was, this is my ignorance speaking, I never quite understood whether what you learned from this specific system was immediately applicable also to all the other systems. And so this comes back to the question that Bernard just asked. If you had one such system of, let's say, a lensed kilonova measured with gravitational waves, how well could you export that new knowledge to all the other systems?
So there's definitely great potential to, so when you have a kilonova, you have effectively, with time delays, you have simultaneously two distance indicators that have covariances in terms of the lensing and the magnification. But that may potentially help tie down other direction in a systematic plane that we have, and that are potentially common among all the lenses. So if you have, if you give me one anchor where you know the absolute luminosity of the intrinsic source, and thus we know the absolute magnification where the images appear, that effectively breaks the mass degeneracy mathematically. And that's currently, we don't have absolute brightnesses of the quasars that, and we never will have, or, you know, depends on what level you trust the most. And so this could, in that sense, be a game changer. Hasn't been seen. Let's see how, and at the end, you need to know it to, you know, 1 or 2% levels. So.
Yeah, I think with lens supernova, the challenge there would be the supernova images would be microlensed by stars in the foreground galaxy, and then you get this noise on the observed fluxes. So it's harder to get out the unlensed supernova flux due to micro. So this has to be accounted for. There's some work starting to look into this, but I think to actually use this double cosmological probe, as what Simon's saying, supernova luminosity distance and lensing distance, I think one has to account for these subtle effects. So there's actually also questions asked in the Slido on the discussion panel that I think it's a top ranked one that I would like to bring up. So it's anonymous, and the person is asking, some have argued for favoring one technique, excluding others, and some for combining multiple independent ones. Which approach do each of you favor?
Everything. Measure it in as many ways as possible. For me, what you can see this in the H0 tension. If you have multiple measurements of the same thing using different phenomena, that's how you discover really interesting new physics. And so I would just say, let's do everything. But the ones I'm particularly excited about are some of the new ones, like the gravitational waves that are sort of an absolute measurement that jumps the distance ladder and has huge potential. And the kind of casual comment that Bernard made that, you know, we're going to be able to see in the sort of couple of generations of detectors time, every merger in the universe is really phenomenal. It's absolutely amazing the power that will have in a decade or two.
Perhaps just to add that the Hubble constant should not be discussed in isolation. I think the Hubble diagram knows about the other cosmological parameters, and maybe there's some hope that as we go to our redshift, we'll learn more about the other parameters. So I think it's another thing to put into the story. Thanks.
We certainly hope with LISA to be able to measure beyond double because we're going out quite far. And so if you go to redshifts of 1.5 or something, measuring W seems to be within the possibilities for LISA.
That's very exciting. Do you see it competitive in terms of, say, W compared with the other standard techniques?
We're talking about what will be the standard techniques 10 years, 10 to 20 years, 10 to 15 years from now. And I don't know what they're going to be. All we can do is, plus we also don't know how many of these mergers we're going to see, what the statistics is going to be with LISA. So all we can do at the moment is say, we think we have the accuracy in individual events to go beyond the Hubble constant.
Yeah, great.
Bernard, how well can you localize with LISA, with these supermassive black holes? How good is the localization?
It's not great, but that's where I think ESA has had the right vision to try to put up Athena so that the two missions can fly, can have some overlap in the time they're flying, because one does expect that the galaxy that's a supermassive black hole binary merger is a disturbed galaxy, and there should be ways of tracking that down.
One thing maybe to go forward, and I'm aware that may be a controversial statement that I'm making here, but I think it's also sometimes time, is it's intrinsically hard to go to 2 and 1% for any of the probes. It's challenging. There's a lot of work in all of the different parts, and this truly needs to be recognized, and I think it is for all the teams that pursue this avenue. The other thing is then, how can we converge eventually? Where are we going to be in 1 year from now? Will the measurements be still some high, some low, and are we getting smarter? And maybe, I don't know, in a year from now, we are here and people publish all their code and data products that allow reproducibility to the level that we currently don't have, that allow people to dig into each other's code and analysis, to go, I want to know what the Hubble constant is. And I know there's a lot of excellent work being done, but I also know it's super hard. And so digging into this, putting it open source, it's about time, in my opinion.
I'd like to pick up something that also came up in the questions, which is also related to one of the earlier questions. So especially in this group where we have such wildly different techniques that are measuring H0, to what degree do you think it's fair to average over these different measurements? Where could be some possible pitfalls when we decide that we're putting in the masers and the gravitational lenses and the distance ladder to determine, and then also standard sirens to determine H0 when they're so different?
Well, if I may try to answer that, that's a generic problem, not only about H0, right? There's a similar issue, say, with sigma 8. What do you do if you have experiments that are a bit further away from each other? When do you decide where they are, the two mountains? When do you decide to average them and end at the valley? So there are various statistical techniques for tension now, or even past year or two, half a dozen or so, that kind of help you to make an intelligent decision when to combine or not. But at the end, there's an element of subjectivity.
I guess the question is whether these are intrinsically measuring the same thing. So if they are measuring the same property of the universe, it's okay to average them and their errors if they're independent. But if it turns out they're measuring something slightly different, which might be true of something like the CMB and the nearby measurements, then we can't average them to get a value because, well, we've now seen that they're discrepant, potentially. And so then it's no longer, then we have to try and explain the differences. So but the differences are intriguing because it really could be that we're measuring something slightly different that's not what we thought that we were measuring with one or the other of the measurements.
Okay, given that we're actually ending at the discussion panel session, does any other panelists want to add more to this question? If not, I'd like to thank the speakers and our panelists again for joining us, and also all the participants. And we will resume our 4th day tomorrow at the same time. So I'd like to say goodbye for today to everyone. See you tomorrow.
Bye-bye.
Thanks, Sherry.
Bye.
Bye.
Bye-bye.
Thank you.
Thanks very much, everyone. Bye-bye.
Bye. Good day.
Thanks all.